Okay, so hello everyone. Can you see my screen and hear my voice? Okay, cool. So, today is our technical session. So in today's lecture, I will talk about the neural networks and deep learning. So, my research background is about neural networks and deep learning and computer vision and natural language processing. So basically, this is my major and topic. So that's why today I will give you the introduction about this part. So, okay, so what is neural networks? So this picture actually illustrates the neural network in a very good way. You can treat the neural network as a Lego. So basically, you can build the neural networks in any way you want, right? You can build the when you build the Lego, you have basic blocks, and you just need to stack those blocks together. So, and in neural networks, it's very similar. But in neural networks, each block is actually a linear classifier. So basically, when you want to build a neural networks, you are basically building stacks of linear classifiers. That's a very simple basic concept of the neural networks. And before introducing the linear classifiers, of course, so let's start from the linear classifiers at first, right? So because, as I mentioned, the neural networks are built by stacking the linear classifier. So we need to introduce a linear classifier at first. But I believe you have to know that very well because at the start of this course, Mingyu has gave you a brief introduction about the linear classifier. And in last semester, you also have the course called machine learning tools. I believe you will also get an idea about the linear classifier and the basic idea of the deep learning. Right? So, before introducing the linear classifiers, we need to know what is the task of classification, right? So basically, linear classifier is for classification, right? So take this image classification as an example. So giving an image, you need to learn a model to classify it into one known category, right? So for example, here is one famous CIFAR-10 dataset. I believe some of you know this very well because I noticed some of you are using this CIFAR-10 as well project dataset, right? So in this CIFAR-10 dataset, we have 50,000 training images and 10,000 test images. And each image in the dataset can be categorized into one of 10 classes, which means we have totally 10 different classes from airplane to truck, right? So, this is not a large scale data set actually. So if you know the ImageNet, COCO, they are quite large and they are, a lot of different classes. For example, in the ImageNet, we have 1,000 classes for the image classification task, right? So in this one, we only have 10 different classes. And the size of this of the image in this data set is quite small, which is only 32 by 32, basically just a small square image, right? And of course, it's colorful image, so which has RGB 3 channels. And this is very small. I mean, the size of the image is quite small, the 32 by 32. But in some other data sets like COCO, it's general images. Some have 600 times 800. Some dimensions may exceed 1,000, right? So this is very small data set. So let's take this data set as an example to learn about the image classification, right? So the most common way we use to classify the image or any other data format is called as a parametric way, right? So which means we need to learn some parameters to classify the data, right? So take this image as an example, it's a cat, right? So we want to learn a parameter matrix W for some functions here, F, with input X. So suppose here X is input. So basically X is image itself, right? And we want to learn some parameters or weights. Basically, it's a matrix. And if we apply this matrix on the image, and then we can get 10 numbers, right? 10 numbers vector, and each number represents the probability that the image belongs to which class, right? So we want to learn some parameters in this way, right? So this function f is basically some predefined classifying function. So this is called the parametric approach. So normally for the data point classification, we can use the parametric approach, right? So if your project, for example, is about, if it is not about computer vision, it's fine. So any machine learning data, if it's a data points, you can use parametric way to do the classification. Well, if your project is about a classification task, right? So for the linear classifier, the function f is simply a linear function. So basically w is the weight matrix, right? And we use w times x. So as you can see, this is just a linear combination, right? So w times x is a linear function, right? So this is called a linear classifier. So basically that means the f, well, the function f decides what kind of classifier you are using, right? So if f is a linear function, for example, times is a kind of linear function, right? So then this classifier is called the linear classifier. So in this case, if we reshape the image, well, here because as we mentioned at the start of this call, at the start of this lecture, we will use the CIFAR-10 image as example, right? So this is a CIFAR-10, a classical CIFAR-10 image. So it's 32 by 32 by 3. 3 is the channel number RGB, and 32 is width, and 32 is height, right? So 32 by 32 by 3. So now if we reshape the image into a one-dimensional vector, right? So 32 times 3 equal to 3072, right? So if we reshape this image into a one-dimensional vector, and this will be the x, right? Because we want to, classify the image into 10 classes. So basically that means our output needs to be 10-dimensional, right? So which means, well, according to linear algebra, so we have to learn a weight matrix, which is 10 times 3072, right? So this will be the size of the matrix you need to learn if you want to classify the image into 10 classes, right? So because 10 times 3072, the matrix, times the matrix, well, here is a vector, which has size 3072, then the output will be 10 times 1, right? So that means the output will be 10-dimensional, and each dimensional basically give us a score of the, of that, whether this image belongs to that class, right? So that's the basic idea of the linear classifier. Of course, normally we will also add a bias parameter in this case, which is just a one-dimensional vector with 10 numbers. So basically a classic linear classifier will be like this: wx plus b, and w and b are the parameters we want to learn. And the size of w depends on the dimension of your input and the dimension of your output, and the size of b will depend on the dimension of your output. Right? So in this case, because our input dimension is 1 times 3072, right? So that will be the size of w, that will be the size of your b. So this is the simplest linear classifier. Okay, so let's again take this image as an example, but here for the illustration, let's just assume there are only 4 pixels. Right, so basically if this image is impossible to be just 4 pixels. Originally we know this is 32 by 32 by 3, right? Now let's just assume it is this data point has 4 dimensions, has 4 pixels, right? Just one channel, and that's a 4 pixel for 56 to 31, 34, and 2. That's input, right? So then we want to classify it into one of 3 classes, right? Let's assume we have 3 classes which are cat classes, dog classes, and sheep class, right? So we want to classify the image into one of these three classes, right? So here, because this is a 4-pixel input, so after we reshape it into this 4 times 1, it will be a vector, and we have, according to the definition of the linear classifier, then the W, the weight matrix, actually the 3x4 matrix, and the input data is a vector with 4 values, and the bias, this is bias B, is just a simple, it's a vector with 3 values. So with the linear function Wx plus B, and we have the output, which is 3-dimensional, which is vector with 3 values. So in this case, well, basically these 3 values give us a score that class belongs to which, that image belongs to which class. So that means, well, the cat score is -96, and dog score is 400, and sheep score is 61. So these scores are calculated based on the current parameters and bias, right? And as we can see, actually, the dog score is the biggest, but the original image is actually a cat. So which means this is not a correct classification, which means the current W is not as good, not good enough, right? So the objective, the whole objective of a linear classification is that we give many and many training examples to the linear classifier, and we want to find out the best W and B so that we can maximize the correct probability, right? So basically, after we learn good parameters W and B, so in some case we will classify it into the right class, the cat class. That means the cat score will be the biggest one, right? So basically, the objective is we want to learn a good parameter W and B so that we can have a really good prediction, right? That's the basic idea of the linear classification, and actually this is also the whole basic idea of the whole machine learning field, right? So we want to learn something, want to learn some parameters from training data, and to give to allow us to make the correct prediction, right? So that's a linear classifier. So well, this figure actually shows the practical meaning of the W and B. So if we plot all the data into a 2D dimensional space, each line we plotted here is actually a linear classifier, right? So basically, slope is W, the intersection is a B, right? So this is Wx plus B. If you learn this, you know, this is I think high school mathematics, right? So this is just a linear, well, a straight line in a 2D dimensional space, right? You have a W and you have a B, you can define this a straight line, right? So basically, these lines or linear classifiers divide the space into several subspaces, and each subspace is actually a class. Of course, in particular, it cannot be only in 2 dimensions. That's simple, right? So here, actually, we just assume the X, the input X is 2-dimensional. So that's why we can have a straight line to divide the space into 2 separate spaces, right? So if above the space is car, below the space is not car, right? But in the real case, the X cannot be just 2-dimensional, right? So as we can see here, if it's 32 by 32 by 3, so basically 372 dimensional. So the dimension in the feature space is super high. So which means it's actually a straight line. That's simple. Of here, it should be some. You need to learn some actually a plan or some, you know, for the high dimensional feature space to divide the high dimensional feature space into 2 parts. Above this part, that's a class. Below this class, that's not a class you want to classify, right? So that's how can we interpret a linear classifier in a 2D dimensional space, right? So of course, the basic assumption of the linear classifier is that the data can be divided linearly, right? So as we showed in this example, all the data points can be classified into, can be divided into two parts, above the line, below the line, right? So this is a linear classification, linear classifier, right? So that's a basic assumption, right? The data can be divided linearly. But in many cases, this is not true. For example, there are three cases in this figure, right? So you cannot simply use straight lines to classify them, right? So for example, this one, numbers, class 1 are the number of pixels bigger 0 odd, and class 2 is numbers of pixels bigger than 0 even, right? So you cannot draw a single line to divide them into two spaces, right? And this circle and this three cluster, right? You cannot find a linear cluster to do that. So which means we need some nonlinear classifiers, right? Okay, so here we already know that the linear linear classifier or linear score function looks like this: f equal to wx plus b, right? So here, for the simplicity, we just ignore the b, right? So let's just assume our classifier is wf equal to w times x, right? So this simplest classifier, and then a two-layer neural network. Now we are transferring from the linear classifier to the neural networks, right? So we know what is a linear classifier now. Now let's go to the neural networks. How can we build the neural networks based on the linear classifiers? But before that, let's find out the issue of the linear classifier, right? So the problem of linear classifier is that the assumption is that the data can be divided by the linear function, right? So, but the truth is that most of the cases we cannot simply divide the data into two parts, or divided by a linear function. So here we need some nonlinear functions, so such as the max. Max is kind of nonlinear function, right? So basically, a two-layer neural network can be defined as this: W2 times max 0 W1x. As we can see, W1x is actually a linear operation, and the max between 0 and this one is a nonlinear operation, right? If you draw the max function into this dimensional space, you will find it is not a linear one, it is nonlinear one. So we gave the nonlinear operation transformation into this formulation, right? And after that, we apply a W2 again on this on the outside the max operation, which means we add another linear layer, right? So basically, a two-layer neural network is linear operation, nonlinear operation, and another linear operation, right? So that's basically idea of the two-layer neural network. So in this case, except the input x and the output s, as represented in a linear classifier, we actually has one middle state, right? So remember, even if we only have the f equal to wx, and x is input and s is output, right? So that's that's a linear score function, right? But here, this is a two-layer neural network. As we can see, we actually add intermediate state. We call it the middle state. So so normally we call it as a hidden state. So in this example, the x is a vector with 3072 numbers, and after the linear transformation with W1, we actually got a vector h with 100 numbers. This is the hidden state. The h is the input to a nonlinear function. Here is a simple max function. So basically, it's just this max function, right? So then the output is equal to another linear transformation with the parameters W2. So as we can say, x times W1 will be equal to the h But here we also need to add a nonlinear operation, which is max. Sometimes we also call it as activation function, right? So after that, we times W2 another linear class, linear matrix with the H, which give us the S. So this is a classic two-layer neural network. Sometimes we also call it an MLP, multi-layer perception. And in this two-layer neural network, we have two linear operations and one nonlinear operations, right? The nonlinear operation is just the max operation. Okay, so this is the simplest neural networks, just the two layers. Now you may ask, well, how about three layers? Okay, it's still very easy. So we have W1x linear, a nonlinear max, a linear W2, another nonlinear max, and the final the linear W3. So this is three-layer neural network. So we have three matrix need to be learned, which is W1, W2, W3. Of course, here we ignore the B, we ignore the bias, but actually, normally for the linear classification, we also have W1x plus B, W2 here plus another B2, W3 plus B3, right? So we also have the bias, but here we just ignore that. Okay, so one question you may want to ask is, why do we call it neural networks, right? So what's just a stack of several linear transformations and nonlinear operations. So what's the connection between the neural networks and our real biological neurons? So let's check this figure. So here is a biological neuron, right? So the cell body is at the central and at the front, and well, the impulses carried toward the cell body actually, and at the back end, the impulses carried away from the cell body. So this is biological neurons. And this lower part actually shows the neural network in machine learning field, just as we talked about, right? So X here is input, and it can be treated as a signal in the real neuron, right? So for example, in your brain, when you accept some signal, it's input, right? So you have to input some signal into your neural, into your eye, because there are lots of neurons in your eyes, right? So basically X is the input. In our case, X might be an image, right? So that means X can be treated as a signal in the real neural, and the input will times by a weight W, which is like the synapse in the real neural. And the summarize operation is like the cell body. So this is a key operation WX plus B, right? So this is kind of summarization operation. Because you may have different input X, which means you have to learn different parameters, right? So the cell body in the real neurons has ability to summarize all these signals and produce some output. So here it's same, right? We have the linear classifiers to summarize everything and summarize them together to produce the output, right? And here, actually, as we mentioned, after a linear operation, we normally add the activation function. The activation function is a kind of nonlinear operation. So in our previous example, we use a max operation as a nonlinear operation as the activation function. But we also have some other very classical neural activation functions, like sigmoid activation function, tangent activation functions, and the ReLU, which is most used activation functions. Okay, so summary so far. So we arrange neurons into fully connected layers, and the abstraction of the layer has a nice property that it allows us to use efficient vectorized code, right? So as we can see in our formulation, we simply represented it as wx plus b, and the dimension of w and x can be varied, right? So that means we have the vectorization format of the operation, which means because in computer, right? In computer, when we do the computation, if we have the matrix, it will be easy to be computed, right? Especially after we have the GPU. GPU is designed for the matrix add operation. So which means it can be computed efficiently, right? So that's why the linear classifier, linear classifier, nonlinear classifier, and the neural network can be easily computed in the GPU, right? So actually, neural networks are not really neural. So as we mentioned, right, they have some connections, but when we talk about neural networks in machine learning, it's not really neural. Okay, so that's about just some basic idea about the neural networks. So now I will introduce the most important part, the convolutional neural networks, right? So we already have the neural networks. Why do we need the convolutional neural networks? So what's the difference and similarities between the neural networks and the convolutional neural networks? So basically, well, I can give you the answer now. The biggest difference is that in neural networks, it's all fully connected neurons, right? So in the convolutional neural networks, well, not all the layers are fully connected. So now let's see the difference. Okay, so before that, before going into more details, let's see a bit of history at first. So the Mach 1 perceptron machines was the first implementation of the perception algorithm. So it's like this. As you can see, it's quite old. So the machine was connected to a camera that used 20 by 20 cadmium sulfide photo cells to produce a 400 pixel image. So this is basically a single camera, right? So that means, for example, if you display, basically this is a pixel. You can treat as a pixel in your image, because Mach 1 perception machine is used for the character classification. So you can treat it as a pixel. So basically, if you display one character by using those lights on the machine, well, it will represent a optical character, right? So the machine is used to recognize that character, and it was designed for recognition letters of the alphabet. And actually, in this machine, in this Mach 1 perception machine, it only actually implemented a simple linear classification, which is just wx plus b. So w and b is the length parameters, and x is your input, right? So give an input which will display on this camera field, and it will this machine will run a calculation of wx plus b, and if we find the value is bigger than 0, that means it belongs to, for example, for example, currently if the machine is trying to recognize whether this is a character B or not. So if the value is bigger than 1, that means he know, well, it's a B. If it's lower than the threshold small, if the wx plus b is smaller or equal to 0, which means it's not the letter B, right? So this is just a simple linear transformation. So in 1960, some people attribute a physical device that implements an early single-layer artificial neural networks. So in this one, they actually add the nonlinear operation. So that's why they call it artificial neural networks, right? So because they also add the nonlinear operation. So this machine is called as Adeline, and a multi-layer network of Adeline units is known as a Madeline, which is another machine. So, well, this part is quite important, which is called the backpropagation. So, well, I don't think today's lecture we have enough time to introduce this backpropagation theory. But this one is important. With all the backpropagation, actually, we cannot learn the parameters, right? So, as I mentioned at the beginning of this lecture, I mentioned that, well, the objective of the linear classification, or objective even for the machine learning, is to learn a good parameter matrix, learn a good W to make a better prediction, right? So you may ask, well, how can we learn W? Right? How can we know whether, how can we, by looking at millions of examples to learn a good W, right? To learn a good weight matrix. Well, this is another story. So to answer that, we need to learn about the optimization, right? So how to give you a loss function, give you objective function, and how can we define use the loss to calculate the gradient, right? After you calculate the gradient, then you will need the backpropagation. You will need the backpropagation to calculate the gradient for each node, for each layer in your neural network. After you calculate the gradient, you will know how to optimize your network, how to optimize your W, right? So, for example, you have the initialization, a random initialization of the W. Of course, you will get better results because the W is not good enough, right? So after you calculate a gradient, well, it depends on what kind of optimization method you are using. For example, the most useful, not most useful. So in most cases, we will use the SGD, the gradient descent method. So when you calculate, after you calculated the gradient, you will know how to use the gradient to find the local minimum of the neural network, which means it will give you a lowest loss, which means it will give you the best accuracy, right? So of course, the whole process, you need to calculate the gradient for each node and for each layer. So how to calculate gradient? You will need a backpropagation. That's why I say the backpropagation actually it is the most important inventory in the neural networks. Well, some of you didn't close your mic. Let me mute you because I can hear some noise. Okay, so let's continue. Yeah, that's a backpropagation. It's quite important, but we don't have time to introduce the backpropagation today. If you want to know about this, you can check you can check the textbook or check the Google. There are a lot of things about the backpropagation. It's one of the most important tricks in the neural networks, actually. Okay, then the neural network in computer vision, right? So my major is computer vision. I'm working on how to recognize images, how to segment images. So that's why here I may want to introduce some history about the deep learning in computer vision, right? So basically, actually, I have to say the neural network in computer vision experienced a long time silent. Actually, until 2006, actually, Hinton et al. Reused this research in some computer vision field, like the face recognition. Actually, when I was a PhD student, I got my PhD degree in 2015. Actually, 2015. It's not far from. It's not far ago. So when I was a PhD student, I know there is something called deep neural networks, deep learning, but I never used that before. When I was a PhD student, I mainly used SVM, a sport vector machine, the GMM, those, we call it classical machine learning tools. Some of you are still use that today for your project, right? So when I was a PhD student, I didn't use deep neural networks. Because at that time, people then think the neural networks will work because it requires large scale of data set, it requires a large computation resources, and at that time we don't have that kind of data set and resources until we have the ImageNet and we have the GPU to calculate everything. So that actually the deep learning, the neural networks in computer vision experience a long time silent until Hinton et al. Actually reuse that, right? So actually this is the key point for the deep neural networks. Basically in 2012, they produced the first strong results on the image classification task by using the deep convolutional networks. That is the most famous AlexNet, right? If you learn the deep learning, you must know the AlexNet, sorry. So in AlexNet, it has 8 layers, so it's one of the most classical. Even people say it's most, one of the first neural networks, right? So Hinton actually, you must know him, right? He won the Turing Award. So Hinton currently is the leading researcher in Google. Basically, you can see Hinton is like the Jobs in deep learning field. He revives this monster, right? So the Hinton et al. Invented the AlexNet in 2012 to run it on the image classification, especially for the ImageNet, and it achieves much better results than the classical SVM-based method. So after that point, convolutional nets are everywhere, from the image classification to the image retrieval. So for the image classification, it's like, well, basically the idea is quite easy, right? So you just want to classify the image into some categories. As we mentioned, CIFAR-10, we only have 10 categories in ImageNet. Classification task, we have 200 cases. 1,000 cases, image and detection, we have 200 classes. And for the retrieval, retrieval is quite different from the classification. In the retrieval, you have a query image, and you want to find out the most similar closed images based on the query image, right? So that's the image retrieval. And we also have the object detection and the segmentation. For the detection, we want to recognize all the objects inside one image and detect and give us a bounding box of that of specific object, and also give us a label, right? And for the segmentation, it's quite similar to the image object detection, but the difference is that in the object detection, you only need to give us a bounding box, right? So in the segmentation, you need to give the pixel labeling. So you need to let me know which, so this pixel belongs to which category. So for example, this pixel belongs to a row, this pixel belongs to a person, right? That's the idea of the segmentation. So segmentation, both detection and segmentations are quite important for the autonomous car driving, right? So currently a lot of starting companies are working on the autonomous driving, right? So that means we need to recognize the person in front of the car, and we need to segment out the road, the traffic sign. So it's all based on the detection and segmentation. And I believe most of the methods are based on the the convolution neural networks, right? Okay, so yeah, as I mentioned here, self-driving is an area that you are using the CNN. And I have to mention the GPU, right? So with all the GPU, we cannot do the neural networks because, as I mentioned, actually, the neural networks is basically a stack of linear operations and nonlinear operations, and all this can be represented as a matrix multiplication, right? So one matrix times another matrix plus a matrix and times another matrix plus another matrix. It's all matrix operation. And the CPU is not designed for the matrix operation, right? CPU is just for linear sequence operation, but the GPU is designed for the parallel matrix operation. That's why GPU, not currently we are all using the GPU for the deep neural networks, right? As you may know, NVIDIA is the biggest GPU producer, and well, of course, it's expensive. It's very expensive. In our center, we have a lot of V100 GPU, but it's quite expensive. It spends about I can't remember millions of dollars to buy a cluster. So that's GPU. Okay, so yeah, well, we talk about the images. Actually, the convolutional neural networks are also used on the video processing and understanding, right? So not only on the images, we also have the videos, like the video classification, video summarization, right? So video is also very important for the convolutional neural networks. And motion tracking. So, for example, we want to detect the joints or the actions of the human. So we need, and sometimes we also need to do the tracking. We want to track the person from one camera to another camera. So it's called video tracking. And we can also use AI, use convolutional networks to play games. For example, the Atari games. So basically, we can train a CNN to the input of the CNN is images, right? It's display the pixels. The input is just the pixels, and the output is actions like turn left, turn right to play games. Actually, the convolutional networks plus the reinforcement learning has produced super good, excellent results on the game playing. Well, it reminds me, actually, some of you are working on the project like using convolutional networks, using reinforcement learning for gameplay, right? So that's CNN for game playing, and people are also using the ConvNet to recognize everything from the from recognizing the largest star clouds to the smallest things such as the traffic signs, right? So basically, CNN convolutional networks are everywhere. So basically, if you want to find a job after you graduated from this degree, so people definitely, I believe people ask whether, do you know the CNN, do you know the convolutional networks, do you know how to use PyTorch, do you know how to use TensorFlow, how to recognize images? So that's basically the current area. I don't like it. Well, machine learning covers a lot of things. CNN definitely, about neural networks, deep learning, CNN are quite important, but it's not just well, the case. It's the key thing of the machine learning, but it's not the only thing in the machine learning, right? But well, people has to use that anyway. So this is actually my field. So I'm trying to combining the computer vision and the natural language processing. So natural language processing, actually, if you check the Twitter every day, you will know there's something called GPT-2, GPT-3, right? So natural language is a different area of the computer vision, right? So in natural language processing, you basically study the machine translation, you study the question answering, text generation, this kind of things. Well, actually, like 5 years ago, or like 10 years ago, people do not use the CNN for the natural language processing, right? People use a lot of traditional classical natural language processing tools like regular expression, parsing tree, those kind of things. But now, well, neural networks such as the GPT-3. It's based on the transformer, which is kind of special neural networks. All NLP, well, most of the NLP applications nowadays are using the neural networks. That means actually we can combine the computer vision and natural language processing because they are using the very similar techniques. So I remember, I will introduce the computer vision and natural language processing combination in one of our case study lectures. So, okay, so well, basically here, one example is called the image captioning. So in the image captioning, the input is image and the output is a text description of the image. So in this case, we need both convolutional neural networks to understand the image, and we need the recurrent neural networks to understand the and even to generate the natural language. Right? That's my current study, and we also have the common nets for arts, right? So left side it shows some images produced by the CNN, right? So I remember one of them sells in a really high price. Actually, someone buy it, right? It's produced by AI. So I don't know what he's drawing. So what the AI is drawing, and this area is also very interesting, which is called neural style transfer. So basically, you have the input image, right? This is input image, the real image captured by our camera, and here is an image. Actually, this is a famous image produced by Van Gogh, and it can actually learn the style of this painting and use the content of this image to draw another painting, and this painting has the content of this one but has the style of this image, right? So we have some more examples. This is quite impressive, and you will see, you will find a lot of applications online, in your app store. Basically, you can upload your own image, and you can choose one style, and it will automatically generate artworks for you. We also have a case study session which is about AI and arts, and one of our researcher called Jamie will introduce how can we use AI to produce music actually to you. Okay, so we spent some time for the history and some different directions in the convolutional networks. Okay. So now let's move to the convolutional neural network, right? So why we want to use the convolutional neural network, right? So okay, so we know the CNN is powerful, right? But why it is powerful, and what is the motivation of inventing the CNN? So we can see that a standard multi-layer neural network is based on the fully connected layers, right? So here, the input layer, the hidden layer, the output layer. If we are talking about the neural networks, basically that means they are fully connected, right? So, for example, in this case, the input is a five-dimensional vector, and each node is a value in that vector. And the hidden state or the hidden layer dimension is 2, and output dimension is 2, right? So from the input layers to the hidden layers, because it's fully connected, so that means we have 1, 2, 3, 4, 5, 6, 7. We have 10. We have to learn 10 different parameters, right? So that's a fully connected network. So basically that means each input unit will connect it to every hidden unit, and each hidden unit will connect to every output unit, right? So this is the fully connected layer we're talking about. This actually produces large numbers of weights. For example, in CIFAR10, right? So in CIFAR10, images are only size 32 by 32 by 3. So basically a single fully connected neuron in the first hidden layer of a regular neural network would have like 32 by 32 by 3, which equal to 3072 weights, right? This is just one layer, right? So from the this is just one layer, and from the input to the one single output directly, right? You will need 3072 weights, right? So this amount is still seems manageable, right? 3000 is not a big number for GPU, right? But clearly this fully connected structure doesn't scale to larger images, right? So for example, in the ImageNet, in the COCO, the normal image is 300, 800, and if you take an image from your camera, it's even larger, right? So sometimes it's more than 1000, and now we have 4K pixels, right? So it will be much bigger, right? So and moreover, we would almost certainly want to have several such neurons, so the parameters would add up quickly, right? So we want to have the numbers of layers. We may have different output classes, right? So for example, well, this network is just a two-layer network, right? So in some cases, for example, if you know the CNN, for example, the ResNet, well, the AlexNet is 8 layers. Then we have the VGGNet, VGG16, VGG19. Now we have ResNet. ResNet has more than 150 layers. So that means the parameters in those in this network, in those kind of large-scale networks are quite huge. Not to mention, well, we may have the output dimension might be well, very huge, right? So we want to divide the image into more than 100 different classes. So that means if we're using just using neural networks, the parameter, the size of the parameters will be super large. It cannot be, it's impossible to be handled by the machine, right? The calculation is too big. So that's why we want to introduce a convolutional neural network. So basically, instead of using the fully connected networks, fully connected connections, we use some convolutional fields, filters, to finish the operation. So basically, the CNN takes advantage of the fact that the input consists of images, and they constrain the architecture in a more sensible way. In particular, unlike a regular neural network, the layers of the convolutional net have neurons arranged in a three-dimensional space, which is width, height, and depth. For example, in our CIFAR10 images, we have 32 by 32 by 3 images, right? So the input will be a 3D tensor, right? Then the neurons in a layer will only be connected to a small region of the layer before it, instead of all the neurons in a fully connected manner, right? So we define a filter which is called convolutional filter. This filter will only focus on a patch of the images, but not each pixels, right? So in this case, we will save some space, save some parameters. So I will talk about it later. Okay, so basically a simple CNN is a sequence of layers. This is a very standard structure of the convolutional neural networks. And every layer of the convolutional net transforms one volume of activations to another through differentiable functions, right? So the differentiable function is quite important. Well, that's because, as I mentioned, as we mentioned here before, we need to calculate the gradient, right? To calculate the gradient, we need to use the back propagation, right? So, well, only differentiable function can has a gradient, right? So if you learn mathematics, so that's why actually all the functions in neural networks need to be differentiable function. well, if the function is non-differentiable, well, sometimes we need to use the policy gradient. Well, it will be another story. In reinforcement learning, we use a lot of policy gradient, right? So here, this is very classic standard structure of the convolutional net. Basically, we have three main types of layers, which is convolutional layer, pooling layer, as you know, the convolutional layer, pooling layer, and the fully connected layer, Well, we also have pooling layers. I'll introduce that later. So let's focus on the convolutional layers at first, right? So this is the most important layer for the CNN, and that's actually why we call it as convolutional neural networks, because we have convolutional layers, right? So, okay, the convolutional layer. Different from the fully connected layer, the convolutional layer only have the local connectivity, right? What's the meaning of the local connectivity? So let's check this. For example, this is a fully connected net, right? So the input dimension is 5, output dimension is 2. If it is fully connected, for each input to is output, I need to have a W, right? I need to learn a W because W times X, right? And well, we also have the bias, but now let's well, forget the bias, right? Let's just have the W, right? So in this case, I need to have 10 different weights, right? Because my input is 5, output is 2, and it's fully connected. 5 times 2 will be equal to 10. Right? I have to learn 10 different parameters. But here, if we are using the convolutional neural networks, we actually in the convolutional networks, it is not fully connected. It is just the local. We only have the local connectivity. For example, here we have a window, right? So in this window, or sometimes we call it filter. In this filter, I don't have. It's not. So I only care about the connectivity inside this window. That means this node, the first node, has no connection to the second output, right? So in this case, here I just need to learn W1, W2, W3 for this one. So this is the local connectivity, right? And the second property of the convolutional networks is called sharing weights, right? So different from the fully connected layers that each connection has a weight matrix, the weights in the convolutional layer are shared, right? So that means this convolutional filter weights is shared with this window, right? So this is W1, W2, W3, and we just simply reuse the weight, here W1, W2, W3. So that means in this case, we only need to learn 3 weight, right? So from 10 to 3, right? So that's the idea of the convolutional neural networks. So okay, so I think we can have rest over here, and let's start at 2:05. Okay. Okay, let's start it again. Welcome back. Okay, so this is a convolutional layer, 2D convolutional layer. So basically, it is a core building block of the CNN. Well, basically, this block actually does most of the computation heavy lifting, right? So let's talk about it into more details. Well, basically, there are three things in one, three hyperparameters, which is height, width, and depth, right? So because we are assuming we are still using the CIFAR10 image, so it will be 32 by 32 by 3, where 3 is the channel size. Okay, so then we have another thing which is called filter, right? So if you remember, as in this example, right? In this example, we just choose a small window to run the linear transformation, right? And this actually, and we in this window we have parameter W1, W2, and W3, and for the same window we can apply the same window or same filter for the other set of the nodes, right? So we call it as a filter, right? So here, basically every filter is just a small spatial layer, but extends through the full depth of the input volume, right? For example, a typical filter on a first layer of a convolutional neural network have a size 5 times 5 times 3, right? So well, this is not well, the size we normally use for the first layer. It's actually same for all different for all different neural networks. We normally use 5 by 5 by 3, right? It's a good enough filter. And during the forward process, actually, we slide more precisely convolve, right? That's why we call it convolutional neural networks, right? This is a filter, and we convolve each filter across the width and the height of the input volume and compute the dot product between the entries of the filter and the input of any position, right? For example, here, suppose that the filter volume have the input volume have size 32 by 32 by 3. So this is a classic RGB CIFAR10 image, right? So if the repeated field, or the here we see the filter size is 5 by 5, then each neuron in the convolutional layer will have weights to a 5 by 5 3 region in the input volume for a total 5 by 5 by 3, actually equal to 75 weights, right? And of course, we also even in the CNN convolutional neural networks, we need to add one bias parameter, right? So notice that the extent of the connectivity along the depth axis must be 3, right? So because we need to actually calculate the dot product between this small patch and this filter, right? So we need to calculate, we need to basically multiply this small patch and this small patch, right, to give us an output. That's why actually the dimension of this, the depth of this must be 3, because the input is 3, right? So as we slide the filter, so yeah, convolve the filter with the image means slide over the image spatially, computing the dot product, right? That's why we call it as convolutional networks. So as we slide the filter over the width and the height of the input volume, we will produce a 2-dimensional activation map that gives us the response of the filter. So basically, this is the input, right? 32 by 32 by 3, and this is the filter, the size 5 by 5 by 3, and we apply this filter on each patch in this image, right? Then after we apply each patch, actually we will have one single output, right? Because we are using the dot product, which is WX and the summarization, right? So which means we will only have one output, and because we slide this filter over all the over each patch inside this image, right? With one pixel as a step, right? As a stride. So which means the output of this operation of this operator and each. So basically, the output of this convolution process, output of this sliding process, will produce a feature map which is 28 by 28 by 1. So later we will talk about why it is 28. Okay. So and actually we can have multiple filters, right? So that means this one is just a filter one, right? So in this filter we can define we can have the parameters, right? Of course we can have another filter which has a different different parameter set, right? Then that means we can produce another activation map, right? So which gave us this green activation map, right? So we can have multiple filters. Now we will have an entire set of features in each convolutional layer. For example, in this case, we have actually 6 5x5 filters, which means we will produce 6 activation maps, right? So because each filter actually will produce a separate two-dimensional activation map, and we have 6 filters, which will give us 6 activation maps, and we will actually stack them together, right? We will stack them together to produce a tensor, and the size of the tensor will be actually 28 by 28 by 6. Actually, this actually gave us a kind of we call it new image, right? So, but the dimension has changed from 32 by 32 by 3 to the 28 by 28 by 6, right? Because here we actually have 6 filters. Well, a convolutional net actually is a sequence of convolutional layers with intermediate activation functions. So basically, when we say what is a convolutional neural network, right? So in the previous slides, we just introduced the convolutional layer. So the convolutional neural networks is actually a sequence of convolutional layers. For example, that's the input 32, 32 by 3. And here, between this one to the output, we define 6 5 by 5 by 3 filters, which give us this intermediate representation. Then we define another 10 5 by 5 by 6 by 6 filters, right? Because current input becomes to 6, right? And we define 10 different parameters, and the size is again 5 by 5, and we convert the parameters on this new image, which actually gave us another new output, which is 24 by 24 by 10. Well, I will introduce why is 24, why is 28, okay? So, and the dimension becomes to 10 because we define 10 parameters, which means, we define 10 different filters, which means we will have 10 different activation maps. We just stack them together, right? And of course, as we can see, the convolutional operation is also a linear operation, right? It's just simply Wx plus b. It's also a linear operation. We don't have the nonlinear operation. So that means actually between this to this, we after the convolution, we actually also add the ReLU, which is a nonlinear operation, right? So we also add the nonlinear operation, so which gave us this stacked layers. We call it as a convolution neural networks. So as we can see, convolution networks is a stack of convolutional layers and the linear operations, basically activation map, activation functions, right? So intuitively, the network will learn filters that that actually activates when they see some type of visual features, such as age of some orientations, or a block of some colors in the first layer, or eventually entire like honeycomb or view-like parameters on high layers of neural networks. So basically the low-level features. So that means if the convolutional layer is more close to the input image, the activation maps actually are more like have higher response to those dots or edges, and if the layers are more close to the output, close to prediction layers, the activation map are more close to the real parts of the image, like human body, or dog's eye, or wheels, this kind of things. So here we show the 32 filters and their activations on given patch. The activation is a convolutional over two signals, and we have explained the connectivity of each neuron in the convolutional layer to the input volume, but we haven't discussed how many neurons there are in the output volume. So well, this is 32 by 32 by 3. So why after we have a 5 by 5 by 3 filter, the activation map is 28 by 28? Of course, 1 is the number of a filter we have, but y is 28 by 28, right? So now let's introduce the calculation formulation, that how can we get the output dimension, right? So here we will show an example that how we slide the filter over the input image, right? So now let's assume we have an input image which is 7 by 7. Of course, well, in this case, the depth is just 1, right? But in the real case, the depth is 3 because we have RGB 3 different color channels, right? And now let's assume we define a filter, the filter size just 3 by 3. And the next step, I want to slide this filter along this X direction, right? And the stride step is just 1. Okay, 1 step. So actually, this is the first one, right? So in the first one, because I can actually, if I run a dot product, right? Dot product means this, the image value times this blue value plus the second image value times the blue value, right? So it's a summarization of WX, right? So which means if I apply this filter on this patch of the image, which will give me 1 value, right? Just give me 1 value. And then I stride it to the next direction, next position. It gave me the second value, then the third value, and the first value, and the fifth value, right? So of course that I can also put this blue filter onto this patch, right? So and this patch, and all if the step size is 1, right? So which means if I have a 7 by 7 input and I have a 3 by 3 filter, and I apply this 3 by 3 filter on this 7 by 7 input with a stride equal to 1, which will give me a 5 by 5 output, right? And now let's try again. Well, the same input image, 7 by 7, and same filter, 3 by 3. But now let's assume the stride equal to 2. That means after I calculate this dot product, I will move 2 steps to calculate the second value. That's the first value. Then move 2 steps, second value. Another 2 steps, third value, right? That means output of this convolution process will give me output which equal to 3 by 3, right? So that's how can we calculate the output. Now, how about we stride 3? Okay, still 7 by 7. Then 3, that's the first step. And the second step, I will move to here, right? So that's the second step. But for the third step, I have no place to move, right? So it doesn't fit. So if you define a wrong stride, actually you will not get a value, right? So you can, basically that means you cannot apply a 3 by 3 filter on 7 by 7 input with stride 3, So here is a calculation. Here is the formulation. The output size will be equal to n minus f divided by stride plus 1. So n is the original input size, f is your filter size, and stride means how many steps you want to move, right? So and plus 1. Okay, so that's the formulation. So in our example, n is input, n is the dimension of the input, which means it's equal to 7, and f is the filter size, which is equal to 3. Now, 7 minus 3 divided and the stride, in our first example, stride equal to 1, right? So 7 minus 3 equal to 4, 4 divided by 1, which is 4, 4 plus 1 equal to 5, right? So in our first case, output is 5 by 5. In our second case, the stride equal to 2. So 7 minus 3, 4, 4 divided by 2, 2 plus 1 equal to 3. So in our second example, remember the output is actually equal to 3. So the output is 3 by 3, right? And in our third example, the stride is 3, and 7 minus 3 is 4. 4 divided by 3, we cannot get the integer, and plus 1 is put on 3, 3, 3, 3, 3, so which is not integer, so which means it's not, it doesn't fit, right? Okay, so that's how can we calculate the output. So in our previous example, n is equal to 32, and f is equal to 3, and the stride is equal to 1. So that means n plus 1, the output actually 28, right? So well, in practical, we also define some actually zero padding, right? So it will be convenient to pad the input volume with zeros around the border, right? So this is original input, which is 7 by 7, and if I decided to pad some zero, just a 1 0 outside at the border of the input. That means the new input of this image will be 9 by 9, right? Because I pad 0 at the left side, 0 at the right side, 0 at the upper side, and the lower side, right? So the nice feature of the zero padding is that it will allow us to control the spatial size of the output volume, right? So if you want to decide how what's the size of your output value, right? So of course, it will depend on your as we mentioned in your function, right? It depends on the filter size and depends on the input, right? If you don't want to change the size of the input, and if you want to stride equal to some fixed number, you can change the input, right? You can change the input size by padding zeros. So here, for example, the input is 7 by 7, and the filter size is still 3 by 3, and we applied with the stride equal to 1, right? So then we pad with 1 pixel border. Then what's the output? So let's calculate it, right? So now the n will be equal to 9, right? Because 7 plus 2 will be equal to 9. 9 minus 3 will be equal to 6. 6 divided the stride will equal to 6 again, and 6 plus 1 will be equal to 7, right? So you see, so after I pad 1 pixel border, and the input, the original input, the image size is 7 by 7, but my output is still 7 by 7, right? So that means the input side and output side is identical, right? This is, it's a 7 by 7 output, right? So the same dimension as the input. This is quite good, right? So most commonly we will add zero paddings with this actually f minus 1 divided by 2 to exactly preserve the spatial size of the input volume. So the input and output width and height are the same, right? For example, if your filter size equal to 3, we normally pad with 0 pad with 1, and if your filter size equal to 5, with 0 paired with 2. If your filter size equal to 7, with 0 paired with 3. And in this case, actually you will get the same dimension as your input for your output, right? So this is good. This is quite good feature for the why? Because we don't want to shrink the volumes too fast, which will make the final result bad, right? Think about this. In this case, we don't use any padding, right? So from 32 to 28, then to 24, to after several layers, right? So original input is 32 by 32, but after adding like 5 to 6 layers, the size of output will become very, very small, right? So even 1 pixel, right? That means you basically you cannot store all the information just into a single value, right? So that's why actually we do not want to to actually shrink the volumes too fast, right? So that's why we want to pad some value, right? So here are some exercises you can do. So for example, input volume is 32 by 32 by 3, and we have 10 5 by 5 filters with stride 1 and pad 2. And what's the output volume size? So let's calculate. You still remember the formulation, right? N, which is n minus f divided by the stride, then plus 1, right? So here the input is 32 by 32, but we pad 2 pixels at the border, so which means the new input will be 32 plus 4, right? So which means it will be 36, and the 36 minus the filter size minus 5 will be actually 31. 31 and the stride equal to 1, so it will be 31 divided by 1 is 31. 31 plus 1 equal to 32. So and we have 10 filters, right? We have 10 filters over here, which means the third dimension will be equal to 10. So the output dimension actually will be equal to 32 by 32 by 10, right? So that's a calculation, right? So the dimension is 32, but we have 10 filters. So the final output volume size of this is 32 by 32 by 10, right? Okay, so how many parameters? The same example, right? Input volume 32 by 32 by 3, 10 different 4x4 filters with stride 1 and the pad 2. So how about so we just calculate how many we just calculated what's the output volume size, right? How about the number of parameters in this layer? Actually, the number of parameters because actually here we have 10 5 by 5 filter, and as we mentioned, only filters have parameters, and each filter have 5 by 5 by 3 parameters, right? Because the dimension is 3. So each filter will have 5 by 5 by 3, and 1 is for the bias, so it's Wx plus B, right? So 1 is for the B, for the bias. So for each filter, we actually have this number of parameters, which is 76 parameters. And we have 10 filters, so the total number of filters is only 760, right? So think about if we are using the fully connected networks. In the fully connected networks, if the input volume is 32 by 32 by 3, and the output volume is 28 by 28 by 3, then the numbers of parameters will be, and we also pad. Okay, we also have the padding. So the input size is 32 by 32 by 3, and because we have the padding, so the output size is still 32 by 32 by 3. Still 32 by 32, right? If you are using the fully connected neural networks, the parameter size will be super large. But here we only use 760 parameters, right? So this is why we want to use the convolutional layers. So, okay, so here is a summarization of the convolutional layer. So basically, we accept a volume size of W1 plus H1, W1 times H1 times D1, this is the depth, right? So basically, if we want to calculate the number of parameters and the dimension of the output, we need to have 4 different hyperparameters: the number of filters, the spatial extent, f, and the stride f. So spatial extent f is basically the filter size, right? And we also need to know the amount of zero padding. So then we, to produce a volume size W2 times H2 times D2, so that's the output. So the W2 equal to W minus F plus 2P, P is the padding size, right? Divided by S plus 1, and the H is same, right? So the height is same as the width, right? Normally the input will be square. So you may consider, you may say, well, our input, for example, how about the real image is like 300 times 800. So how to calculate it? Actually, in the convolutional networks, before we send the image into the CNN, into the input layer, we first squeeze the image into a square, right? So and the D2, which is equal to K. And with the parameter sharing, it introduces F times F times D1 with parameters. Of course, you need to add in the bias, right? And in the output volume, the D-step slice is the result of performing a valid convolution of this filter of the input volume from a stride S, right? That's a summarization of the convolutional layers. So, actually, the one-by-one convolutional layer will make perfect sense. For example, an input tensor with 56 times 56 times 64, and after one-by-one convolution with 32 filters. One-by-one convolution means the filter size is just 1 by 1. So basically, that's a pixel, right? So that's so you just run it pixel by pixel. Then actually that will be same as fully connected layers, right? So actually this will give you 56 by 32 output, right? Because you have different 32 different filters, right? Okay, so from the neuron view to see the convolutional layer, it's just a neuron with local connectivity, right? Where X is the input image pixel and W are the filter, filter parameters, right? So in this case, activation map is a 28 by 28 sheet of neural outputs, and each neuron is connected to a small region in input, and all of them share parameters because the same filter will convolve the whole image, right? Remember, in the neural networks, actually, it focus on the 1 pixel by 1 pixel, 1 value by 1 value, right? But here, because we have the concept of filter, so that means each filter only focus on a part of the image, a part of the input, right? Just to focus on a patch, right? And because we also have the parameter sharing, so the same filter will convolve the whole image, right? As we mentioned, for the convolutional neural networks, normally we don't only have one filter. We can define multiple filters. And if we have, for example, if we have 5 filters, the convolutional layer consists of neurons that are arranged into a 3D grid. It means that there are 5 different neurons all looking at the same region in the input volume with different things, right? So that means well, we have different filters may want to deal with different different information. Right? For example, some filter is looking at the color, some filter looks at the edge. So different filters may have different functions, right? Different filters may have different like your neural in your brain, right? Different may have different functions, right? Okay, so we quickly introduce the convolutional layers. Now we also have, well, ReLU basically is just an activation layer. It's a kind of a nonlinear function. So because we know the convolutional layer is kind of a linear operation, so we need to add the nonlinear operation, right? And we also have the pooling layers, right? So basically it's common to periodically insert a pooling layer in between successive convolutional layers in a convolutional network architecture. Its function is to progressively reduce the spatial size of the repetition to reduce the amount of parameters and the computation in the network. And it also controls overfitting. So overfitting is a problem in neural networks. So when we have large numbers of parameters, during the training, it may fit the training data very well, but come to the testing, you because you may have this distribution shift issue, it doesn't work on the work very well on the testing set, right? So we can, in that case, we can introduce a pooling layer. So the pooling layer, actually for pooling layer, we have different types of pooling layer, like average pooling, max pooling. So basically the pooling layer operates independently on every depth slice of the input and resides in the spatially, which makes the representation smaller and more manageable. For example, for some pooling layers, we can downsampling original size from 224 to 112, right? Just to decrease half of the size. It depends on how you define your filter size. Okay, so for example here, this is just a single depth slice. Well, but normally we will have several slices, right? So that's the depth, right? So and here let's assume we are using the max pooling with 2x2 filters and stride 2, right? So that's a 2x2 filter and it's a max pooling. Max pooling means in this window I will only choose the max value to represent the values inside this area, right? So in this 2x2 window, the biggest value is 6, so I put 6 over here, and because stride equal to 2, so that means I can move the window into the filter into the next this green part, and the biggest one is 8, so 8. This part, the biggest one is 3, biggest one is 4, next part, and then 4, right? So that actually, as you can see, the original size is 4x4. Now the new size is 2x2, right? By using a 2x2 filter and stride equal to 2, we decrease the original size into half, and we only pick the biggest value. This is called as well the max pooling. And we also have sometimes people are using the average pooling. Average pooling means we calculate the average inside this window, right? So it's 1 plus 1 plus 5 plus 6 divided by 4. Then use the value to represent this small patch. Right? That's a pooling. So well, for the pooling layers, we also have some calculation rules. So, for example, the input volume is W times H times D, and well, we require two hyperparameters: the spatial extent, basically the filter size, and the stride S, and the output W equal to the W1 minus F divided by S plus 1, which is actually equal to the convolutional operation, right? And here for the pooling, we will not add the padding, right? Yeah. Yeah, it's not common to use zero paddings for the pooling layers, right? So that means you need to carefully design your filter size, right? Okay, then finally, don't forget we also have the fully connected layers, which contains neurons that connect the entire input volume, as in ordinary neural networks, right? So normally we only have the fully connected layers at the end of the neural network, because fully connected layers just take so well. It there are so many parameters in the fully connected layers, right? So that's why we don't want a lot of fully connected layers. We only add it at the end of the neural network, right? Yeah, so here is a fully connected layer, which is just a simple simple neural networks, right? Input, for example, we introduced this before, right? Input is, if this is input, then we receive into one vector, then just WX, and sometimes we plus a B, right? The activation map will be this value, right? Okay, so, basically, for the convolutional networks, we have basically it's a stack of convolutional layers, pooling layers, and fully connected layers, right? We use sometimes to introduce convolutional layers, and the pooling layer and fully connected layers, connected layers are just neural nets, neural networks, right? And the pooling layer is quite easy, right? And the current trend in the well, you may think about how should we define a convolutional network, right? So how can we know how many convolutional layers we have, how many the fully connected layers we have? So there are some designing trends. So many research work are trying to study how can we design effective neural networks. And recently, actually, some people are working on automatic design neural networks or convolution neural networks based on the input data. Right? But a trend is that towards smaller filters and deeper architectures. People already find that if the architecture is deeper, well, the results are better, right? And people tend to use smaller filters because you can have you will have smaller patch to look at, right? And and another trend is towards to getting rid of pooling and fully connected layers by just using the convolutional layers. Well, for the pooling layer, it's the results. The reason that we use pooling layer is that well, at some step we can decrease the size by half, right? So, but because now we have more and more GPU memory, so we can actually use the convolutional layer to decrease size as well. So now actually less and less people are using the pooling layers, but sometimes we still need it. And the typical architectures of the convolutional networks is like this. We have one convolution, we have a convolutional layer and then a ReLU layer, right? Remember, the convolutional layer is only the linear operation, and the ReLU is a nonlinear operation. And this we can stack this with n layers, right? And sometimes we also have a pooling layer after n stack of this convol and the ReLU layers, right? And this block can repeat like m times, right? So m different blocks. So as here, right? So convolutional ReLU, it repeat 2 times, and we add the pooling layer. And actually, this block, this convol ReLU pool, repeat 3 times. This first time, second time, and third time, right? So we can repeat it. And we also have the fully connected layer and the ReLU layers, and it can repeat several times. But as I mentioned, we don't want the k too big, right? Because if k is too big, then that means we have too many parameters. And finally, we will have the softmax layers. Just one softmax layer, because softmax layer can can change the vector into a vector that's a summarization of the values in that vector equal to 1, which are more like a probability of the value, right? So where n, this one is really up to 5, right? So n is just normally smaller than 5, right? And m can be large, right? So we can have many blocks. And k, the number of fully connected layers must be very small, normally small and equal to 2, right? So in this case, actually in this case, I think the n is equal to 2, right? Because it's repeat once, repeat twice, and the m, the big M is actually 3. 1, 2, 3. I will repeat it 3 times, and the fully connected layer is just 1. We only have 1 fully connected layers, right? Well, this is actually a typical architectures, but recently advances such as RescueNet, GoogleNet actually challenge this paradigm. They are trying to define some other different structures and still can make better results. For example, some works are trying to investigate whether we can make the network wide but not deep to make it works better. So as I mentioned, there are some other works trying. It's called neural architecture search. It tries to it doesn't predefine a structure for the CNN. Instead, they define some neural network to learn to how to design a structure for another task. It's called neural architecture search, which is quite a hot area in current machine learning field. Okay, thank you. So I think that's it. That's the end of today's lecture. Basically, I start from the linear classification and introduce the neural networks. The neural networks is basically stacks of the linear classification with some nonlinear operations. Then I introduce the history of the convolutional neural networks and some cases that why we how can we use the convolutional networks to computer vision applications. Then we introduced why do we need the convolutional neural networks, right? Because the parameters in the neural networks are too large for the computer vision applications, right? Because the image size input is quite big. Then we introduce what's the filters, how to convolve the filters, and what's the formulation to calculate the output size, parameter size based on the different size of the input and different size of the input and numbers of paddings, this kind of things. And we also quickly introduce the pooling layers. Yeah, that's it. Okay, thank you. So, any questions? Okay, thank you. Okay, so if no questions, I think that's today's lecture. And if you have any question, anyway, just email me or send me put it on the discussion channel. Okay, so would you suggest any further resources for these topics? You mean the CNN, the convolutional networks? Well, let me show you this page. Let me find, yeah, this one. This is super good. Let me find whether this website is still here. No, this is yes. Let me stop share my screen and share my window. Yeah, okay. Yes, this is a Stanford course. It's called CS231N. This is quite good. Actually, I started CNN from this website because, as I mentioned, I didn't know anything about the deep learning, about the neural networks when I was a PhD student. After I became a postdoc at Adelaide, actually, I started to learn the deep learning by myself, and this is a perfect start of the deep learning. This is super good. I suggest every my student to check this website to learn about everything you need to know about the CNN. And of course, if you want to know more deeper details, like recurrent neural networks, reinforcement learning, and more kinds of things, you'd better find some textbook or other resources. But this one is quite good for a starter. Okay. Yeah, this is course given by Fei Li. I think you can just CNN Stan for this one, CS23, and this is super good. And this course is given by Fei Li, who is one of the best researchers in this world currently, and a lot of female students of her. And it also includes some assignments, and you can also join the discussion, which is quite good. Here have the detailed syllabus and the course notes. Yeah. Okay, that's it. Okay, thank you. If you have any questions, just let me know. Okay, bye.